Hello students, welcome back to Sapphirebluechemspark. Let us start our today's session, the chapter Coordination Compounds from Inorganic Chemistry. The previous sessions we have completed some of the topics from coordination compounds. Those are introduction part, Werner's theory, important definitions of coordination compounds and its nomenclature. Today we are going to discuss about isomerism in coordination compounds. Actually, isomerism can be exhibited by organic compounds, where we discussed about the isomerism of organic compounds in two different ways. One is structural isomerism, the other one is stereoisomerism. Similarly, some of the inorganic compounds can also have a tendency to exhibit isomerism. That is what today we are going to see in our coordination compounds. Okay, what do you mean by isomerism? Isomerism is a phenomena in which the same molecular formula of a given compound can have different structural formula. So, as far as considering the coordination compounds, the central metal ion is surrounded by the ligands, a group of ions or molecules. So, homoleptic complexes as well as heteroleptic complexes we have depends upon the composition of this coordination entity. Let us find first of all structural isomerism. The structural isomerism of coordination compounds, those are broadly divided into four different types of isomerism. Those are ionization isomerism, coordination isomerism, linkage isomerism and solvate isomerism. First of all, let us see ionization isomerism. Ionization isomerism in which the compounds have the same formula but its solution can give rise to different ions. So, let us take an example of ionization isomerism. Here I have taken pentaamine chloridochromium 3 sulfate. When this complex is taken in solution, it is split up into this coordination entity along with sulfate ion. In this case, the sulfate ion and the chloride ion, they can exchange themselves. This is the sulfate ion of counterpart of this complex, and here the chloride ion is the ligand of the central metal ion. So, the ligand of the central metal ion which can exchange with the counter ions of the complex. So, what will get? Chromium NH3 5 times, SO4 and the Cl that becomes the counterpart of the ion. So, the sulfate ion and the chloride ions that can exchange themselves. So, we will get the complex of the type pentaamine sulfatochromium 3 chloride. So, here when these complexes are taken in solution, we have the coordination entity. Besides that, sulfate ion and chloride ions, the different counter ions are formed in aqueous solution. How the presence of these ions can be identified? Sulfate ion that answers for barium chloride test and chloride ion that will answer for silver nitrate test. So, based on the simple chemical test, we can identify what kind of counter ions those complexes possess. So, this is what ionization isomerism, in which the counter ion or the simple anion and the ligand of the entity, coordination entity, they can exchange themselves, that gives rise to different ions in solutions of those complex compounds. Then next one, coordination isomerism. Coordination isomerism is possible where both of the entities are complex entities. Complex means the one will be the complex cation, the other will be the complex anion. So, complex cation is made up of a neutral ligand and the complex anion made up of anionic ligand. Such a way, the ligands they can exchange among the metal ion. So, that gives rise to coordination isomerism. Let us find this is hexaamine chromium whose oxidation state is 3. Hexacyanidocobaltate 3. So in this case, the chromium complex has +3 state and this is -3 state. Now these complexes, they do exchange their ligands. So cyanide goes to chromium and ammonia exchanged with cobalt. So where the ligands exchange, the charge of the complexes will also be observed. Here hexaamine cobalt 3, hexacyanidochromate 3 it comes. Okay. So these coordination isomerism can be exhibited by the complexes of the type where they have both cationic and anionic coordination entities. In this case, the ligands are exchanging themselves between the cation and anion entity. As a result of that, we are getting its isomer. The next one, linkage isomerism. Linkage isomerism arises out of the difference in the attachment of atom of one of the donor. One of the donor is the ligand. So we know ambidendate ligands. Ambidendate ligands, they have more than one atom, have a tendency to donate its pair of electron to the central metal ion. So in such cases, we may find two different donor atoms. Such type of ligands, if at all present in the complex, they may give rise to linkage isomerism. So the two possible ways of attachment of a ligand to the central metal ion, it is possible only by the ambidendate ligands. So we can take an example of the complex type pentaamine nitrito, because it is a nitrite group, nitrito cobalt 3 chloride. In this case, I have given NO2 group where the nitrogen is directly attached to the cobalt ion, and this NO2 that can be represented in its another form, that is isomeric form only, that too. Actually it is ONO type. Here the oxygen is directly bonded to the cobalt, not the nitrogen. So here how will we write the complex? Pentaamine nitrito O cobalt chloride. That means O cobalt 3 chloride we will write. So the structure of these complexes we can represent such a way. In this case, the cobalt is surrounded by the 5 ammonia ligands. Along with the NO2 group, you may find the NO2, the nitrogen is directly attached to the central metal ion. Similarly, you can represent the structure of this complex where the oxygen is directly attached to the central metal ion along with the 5 ammonia molecules. So such a type of isomerism arises out of the difference in attachment of donor atoms of a given ligand, is said to be linkage isomerism. The next one, solvate isomerism. Solvate isomerism, in which depends upon the solvent molecules, where the solvent molecules can behave as a donor group, or even they can present as a water of crystallization to the crystal compound. So whatever they composed of with the coordination entity, they give rise to different colors. So depends upon the number of water molecules, whether it is present as the ligand or simply present as a water of crystallization, we may find different colors of the complexes. So in this case, we have taken the solvent as water. In place of solvent, if at all you have taken water as the solvent, then that isomerism is said to be hydrate isomerism. So in this case, the water that can be directly attached to the central metal ion, or even they can present just to the part of the crystal lattices, we may find the different color depends upon its composition. So let us find the example. Hexa aqua chromium 3 chloride I have taken. So in this case, all the 6 water molecule that behaves as the donor group of central metal ion. So now I am going to exchange the chloride ion with the water molecule. So one of the chloride that enter into the coordination entity and one of the water molecule displaces. So we will get penta aqua chlorido chromium 3 chloride, where the color of the complex is blue green, but in the previous case when all the ligands are water molecule, the color is violet. Similarly, when one more chlorine atom is exchanged by the water, I will get tetra aqua dichlorido chromium 3 chloride dihydrate, because the two molecules of water is present in its crystal lattices itself. So for this we can write the name of the complex penta aqua chlorido cobalt. It is a positive complex, that's why it is cobalt 3 chloride. How many water molecule it has? One water molecule, so it is monohydrate. But in this case it has tetra aqua dichlorido chromium 3 chloride dihydrate you have to write. So while naming the complex, if at all water molecule is present as the water of crystallization, those always to be taken in its IUPAC nomenclature. That's all the different forms of structural isomerism. Stereoisomerism in coordination compounds. Stereoisomerism further broadly classified into the two types of isomerism. One is geometrical isomerism, the other one is optical isomerism. This geometric and optical isomerism arises out of the difference in spatial arrangements of the ligands about the central metal ion. So first of all, let us find geometrical isomerism. Such isomerism can be exhibited by the complexes having the coordination number 4 or greater than 4 only. So let us find first of all geometrical isomerism. Geometrical isomerism can be exhibited by the complexes having the coordination number 4 and 6. Let us find first of all the complexes having coordination number 4. So when we write coordination number 4, the ligands that might be 4 different ligand or 2 of them similar, 2 of them different, so that can have different ligands can have. So geometrical isomerism can be given only by the heteroleptic complexes, because I have given A2X2 type, A2XY type, ABX2 type, ABXY type. In all these cases, we are finding only the 4 ligands. At the same time, one of the ligand present twice the time, the other ligand present twice the time. So this complex is said to be heteroleptic, and these are also heteroleptic. So geometrical isomerism can be exhibited only by the heteroleptic complexes in which the coordination 4 is taken, and the coordination number 4 having the complexes of the type given, where A, B are taken as neutral ligand and X, Y are considered as negative anionic ligands. So just for consideration, I am just giving A, B are referred as neutral and X, Y are referred as anionic ligand. Okay, let us find the complex of the type. Okay, when the coordination number is 4, the geometry of the complexes can be of square planar or tetrahedral, but geometrical isomerism can be given only by the square planar complexes. But the tetrahedral complexes do not show geometrical isomerism. This is because the relative positions of the ligands with respect to each other will be the same, and hence we can't be able to distinguish the spatial arrangement of the 4 ligands with respect to one another, and hence we are saying geometrical isomerism cannot be exhibited by the complexes having tetrahedral geometry. Okay, let us find the complex of the type Ma2X2, where I said A are neutral ligands, X are anionic ligands. So having the type of complex diamine dichlorido platinum 2. Here its oxidation state is 2. So in this case I have 2 amine molecule and 2 chloride ions. So these ammonia and the chloride, they may find different spatial arrangement about the platinum ion. So in this case platinum, to which 2 of the ammonia molecule are of same side and 2 of the chloride ions are of the same side. So here as these ligands to the same side, such isomer is said to be cis isomer. And if one pair of the ligand they find diagonally opposite to each other, then that isomer is said to be trans isomer. So due to the difference in the arrangement of the groups about the central metal ion, they give different colors to the complexes. For cis isomer, the color attributed with the complex is pale yellow. But the trans isomer, it has dark yellow. So as they are differing in their spatial arrangement, their properties of the complexes will also be differed. So it is not necessary the property of the complexes to be same. Okay, the next type, let us find Ma2XY type, where A is the neutral ligand, XY are anionic ligands. So we can have the complex of the type CONH3 twice ClBr. Chloride and bromide are anionic ligand and ammonia is a neutral ligand. In this case, the complex having 0 oxidation state, therefore the oxidation state of cobalt will be 2, then only the entire oxidation state will be equal to 0. For this you may find the 2 of the ligands which are same, if at all are on same side, then we can say this is what the cis isomer, and the same ligands if at all diagonally opposite to each other, then it is said to be trans isomer. Okay, how will you name the complex? You should write cis diamine chloride, cis diamine bromido chlorido cobalt 2. This is trans diamine bromido chlorido cobalt 2. So when we write the IUPAC nomenclature, we should write what type of geometric isomer that complex exhibits, that also to be included. Let us find the next complex of the type MABCX. In this case, all the 4 ligands are different, and such a type of complexes are capable of forming 3 different isomers, and in these cases one of the ligand is used to be fixed in a position. With respect to the fixed position of the ligand, the other ligands will be referred. So we can say if one of the ligand is fixed, then it is taken as A. And with respect to A and the ammonia is trans, so I can say this is as B. So their name is generally represented as A trans to B. Such complexes usually termed as A trans to B. That means A is the fixed position and B, with respect to A, you are viewing the B and saying it is trans to the group A. So in this case, NH2OH is taken in its fixed position. So those are the A group. With respect to A, you are identifying NH3 becomes trans to hydroxylamine, and the pyridyl group trans to hydroxylamine, and the NO2 group becomes trans to hydroxylamine. So this is a special pattern of the geometric isomerism having the coordination number 4. So such a type of complexes able to form 3 isomers. One is fixed. With respect to fixed, the rest of the 3 ligands they bring to their trans position to A. So I have besides NH2OH 3 groups are there. All these 3 groups given to the trans to A. The complexes forming the different isomers said to be A trans to B. The next type of the complex MAB2, where AB is a didentate ligand and it is didentate ligand, so 2 into 2 the coordination number becomes equal to 4. So for this complex let us take an example of bis glycinito platinum 2. So in this case the oxidation state of platinum is 2. Glycinito is nothing but NH2CH2COOH. Actually it is glycine. Glycine formula NH2CH2COOH. So one is the amino group, the other one is acid. So these are the class of amino acid. And this amino acid is the first member of amino acid because we have 20 amino acid. So in this case when I remove one of the hydrogen it becomes the anion and this nitrogen has a lone pair electron and the name of the compound is glycine. So from this the hydrogen proton is removed, so anionic part, that's why the name is given glycineto. And here one neutral part and one anionic part I have, so both of them able to donate the electron pair to the central metal ion and hence it is said to be a didentate ligand. So in this case, such cases you may find when NH2 to the same side and oxygen to the same side. This is a single group, this is another single ligand. Both of them are bonded to the platinum through NH2 and through oxygen. So here NH2, NH2, oxygen, oxygen are of same side. This is same. When we write trans to the position, NH2 trans to NH2, oxygen trans to oxygen. So this is said to be the cis isomer of the complex and it is said to be trans isomer of the complex. That's all. The geometrical isomerism exhibited by the complexes having coordination number 4. Next one. The complexes having coordination number 6 can also exhibit geometrical isomerism. One of the type of complexes having coordination number 6 is MA4 type X2 type, where A is the neutral ligand, X is the anionic ligand. Octahedral complexes usually formed by the metal ions having the oxidation state 3, 4 only. Except osmium. Osmium can have that octahedral complex in its +2 oxidation itself. Square planar tetrahedral complexes where the element metal ion is usually in +2 oxidation state. Octahedral complexes, the oxidation state of central metal ion must be +3 or +4. Exceptional case is osmium complexes in which osmium can have +2 oxidation state. So we are going to take the complexes having the central metal ion +3 state and +4 state only. The first type of the complex for which tetraamine dichlorido cobalt 3 ion is taken. And in this case 4 of them are ammonia molecules and 2 of them are chloride ions. So with respect to the position of chloride ion, we can classify whether the isomerism is the cis form of geometric or trans form of geometric isomerism. So when I write that octahedral structure, we can numbering the position 1, 2, 3, 4, 5 and exactly the position opposite the down the plane is 6th position. If the ligands are in 1,6 position, that is said to be trans position. Or if the ligands are present in 1,2 position, you can give numberings this way or even anti-clockwise way. Any direction you will get 1,2 position or 1,2 position. So just observe the 1,2 position for the cis isomer and observe 1,6 position for the trans isomer. So in this case, I can write the 1,2 position. So 1, 2 or 2, 3 or 3, 4 or 4, 5, all of them are cis position except 1, 6 position. So here I have the chloride are of same side, that is a 4, 5 position. So this is said to be cis isomer. The same chloride ion, it is taken in 1, 6 position, that is said to be trans isomer. And the next one complex of the type A3X3. where 3 of them are neutral ligand, 3 of them are anionic ligand. And in this case, the position of ligands, the similar ligands, if at all occupies the same face of the octahedron, that isomer is said to be FAC isomer. So such complexes of the type will give rise to FAC and MER isomer of the geometric compound. Geometric isomerism. How FAC and MER is identified? FAC means facial, MER means meridional. Facial, where we are finding the faces of octahedron. If the 3 similar ligands are occupying the faces of octahedron, such isomer is said to be FAC isomer. Or the 3 similar ligand, when they are occupying the equatorial position of this one and this one are said to be axial position, and the 4 bonds which are lying on a plane are said to be equatorial position. So we have 1, 2, 3, 1, 2, 3 equatorial position. So when the same ligands occupying the equatorial position, such complexes are said to be meridional isomer. So depends on the similar kinds of ligands occupying either the face of the octahedron or the equatorial position of the octahedron, they are classified as FAC isomer and MER isomer. So by writing the complex, you may find the 3 chloride ions which are occupying the same face of the octahedron, as well as the 3 ammonia molecules occupies the other similar face of the octahedron. So this isomer is said to be FAC triamine trichlorido cobalt 3. This one MER isomer, because the 3 similar chloride ions occupies the 3 equatorial position of the octahedron. So it is MER triamine trichlorido cobalt 3. Then complexes of the type having a didentate ligand and a unidentate ligand. So didentate ligand usually represented as AA, twice the time, and the unidentate ligands twice the time present. For this we can have an example of dichlorido bis ethane 1,2 diamine cobalt 3. Here oxidation state is 3. In this case oxidation state is 3. Here also the oxidation state of central metal ion is 3 only. So for this isomer we can give the 2 different forms, cis form and the trans form. So when same ligands are of same side, that is the 1 position and the 2 position, 1, 2 position of the octahedron occupied by the chloride ligand, so it is said to be cis isomer. And the 2 chloride ions, they occupy the 1,6 position of octahedron, so this is said to be trans isomer. The next type, here this ligand is an unsymmetrical ligand. This ligand is symmetric. You can find out about the CH2 group, you have similar NH2 and NH2. But in this glycine, about the CH2 you have NH2 group, other side you have carboxylate group. Such type of ligands are said to be unsymmetrical ligand. So when these unsymmetrical ligands are present in the complexes of the type, we have tris glycinato chromium 3. Here also the oxidation number is 3, where we have to identify the position of nitrogen and oxygen alone. So in this case you may find oxygen, nitrogen, they are exactly opposite in their 1,6 position. And nitrogen, oxygen in their equatorial position also, the elements, the binding atoms of oxygen and nitrogen are opposite to each other. So this isomer is said to be a trans isomer. But here you may find the oxygen atom of that one of the glycinato is similar to the 6th position of glycinato. So OO, NN. So these 2 positions are similar and hence this is said to be cis isomer. That's all. The geometric isomerism exhibited by the complexes having coordination number 4 and coordination number 6. So under stereoisomerism we have one more isomerism termed as optical isomerism. Optical isomerism also exhibited by organic compounds whose aqueous solutions capable of rotating plane polarized light in clockwise direction or in anti-clockwise direction. That gives rise to the two different isomers, dextroisomer or levoisomer. Similarly, cis form of geometrical isomers also exhibit optical isomerism. So, under optical isomerism, the complexes having coordination number 4, also the geometry is square planar, does not exhibit optical isomerism because the square planar complexes have plane of symmetry. So, to exhibit optical isomerism by the complexes, we have to consider the two important points. One is that plane of unsymmetry and that non-superimposability. So, plane of unsymmetry, that is termed as chirality of the molecule, and the image and its molecule never be superimposable. So, the complexes satisfying the two conditions of chirality and non-superimposability can exhibit optical isomerism. The complexes having coordination number 4 with the geometry of square planar possess the plane of symmetry, and hence square planar complexes do not show optical isomerism. But the tetrahedral complexes with the unsymmetric bidentate ligand of that glycineto exhibits optical isomerism. This alone that exceptional case. Next, let us find the complexes having coordination number 6. So, in coordination number 6, the complexes of cis isomers alone exhibit optical isomerism. Trans isomerism never exhibits because of its plane of symmetry and that molecules becomes achiral. So, cis isomer of geometrical molecules only be chiral, and hence those alone exhibits optical isomerism. So, let us have the complex of the type MAAX2Y2 type. So, one of the ligand is didentate, the other two ligands are other kind of ligands are unidentate ligands. So, we have the complex of the type COEN NH3 twice Cl2. So, diamine dichlorido bis ethane 1,2 diamine cobalt 3 whose charge is +1. So, we may find the NH3, Cl and En. En can be represented like this because this end is NH2, this NH2 and the rest of the curve it represents CH2, CH2 linkage. So, we can represent the just curve line for the ethane 1,2 diamine. So, when we write the cis form of this, you can find its mirror image. When this image keeping over that, they become non-superimposable. So, it exhibits optical isomerism. Similarly, the complex of the type MAA2XY. Two of the ligands are didentate and the other two ligands are unidentate. So, in this case, we can take complex of the type X2 where other two ligands are similar unidentate ligands. So, example of the complex is dichlorido bis ethane 1,2 diamine cobalt 3. Here also the oxidation state of cobalt is 3. So, here 1,2 position chloride is there. So, it is the cis isomer and other positions are occupied by the bidentate ligand. Its image becomes this is. So, the image and the molecule not superimposable and hence this form exhibits optical isomerism. The next type is where all the ligands are bidentate ligands. So, in this case we have taken tris ethane 1,2 diamine cobalt 3. Here the oxidation state is 3. So, you can represent all the 6 positions of the regular octahedron occupied by ethane 1,2 diamine and its mirror image exhibits like that. So, the image and the molecule do not superimpose each other. So, this kind of molecule also exhibits optical isomerism. That's all. The isomerism exhibited by the coordination complexes. We discussed about structural isomerism as well as stereo isomerism. Okay students, let us close our today's session and we will continue the same chapter in our following sessions. Until then, bye bye.